A graph data structure is a nonlinear data structure consisting of vertices and edges. They're used to solve many real-world problems and are commonly needed to solve coding challenges. Harris from Coding Cleverly teaches this graph course using Java. Harris is extremely knowledgeable in algorithms and data structures.
Hey there everyone, this is Coding Cleverly, and today we're going to be talking about the graph data structure. We're going to talk about how it works, how it's constructed, and all the important stuff we need to know about it. The first thing I did was create 3 different files in the same directory. Here I have graph.java, and then we have vertex.java, and we also have edge.java. And what I'm going to do now is I'm going to actually write some code, and then I'm going to try to interlink these all 3 files, because this edge, this vertex, and this graph are going to be used together to create our graph data structure. Before talking about graphs, I want to talk about the graph traversals. There are many ways to traverse a graph, but you will focus on 3 methods: depth first search, breadth first search, and Dijkstra's algorithm. These traversal methods are core algorithms for searching a graph. Now, what are graphs? Graphs are the ideal data structure for modeling networks, making them an essential part of your data structure toolkit. They are made up of nodes or vertices which hold data and edges which connect to vertices. A vertex is a single node. Now all of this will be explained through the diagram. Here's a sample of a graph that I created. These circles everywhere are actually vertices and they're holding data. And edges which connect to vertices. So these lines over here are known as edges, these things. Now I want to give an example. Consider a map of your neighborhood. As a graph, we could represent bus stops as vertices and bus routes between stops as edges. So how about the internet? Web pages can be thought of as vertices and the hyperlinks that connect them as edges. Real-world relationships represented as graphs are numerous, making them an important concept to grasp. The graph which you could see over here is actually representing a social network. People are vertices and edges are friendships. So these lines are friendships, these circles are the people. Peter, Cody, and Jordan are all friends. Peter and Cody are friends, and the same goes for Cody and Peter. Peter and Jordan are also friends, and Jordan and Peter are friends as well. So this bidirectional pattern is also existing here. Jordan and Cody are friends, and Cody and Jordan are friends. One other thing that we see here is this thing, which is Caleb and Alex. Now these are friends, but these are not linked with these people over here. Interesting. A path is made up of vertices connected by any number of intermediate edges. From Peter to Cody, the paths could be Peter to Jordan to Cody or Peter to Cody. There is no way between Peter and Caleb. A graph is disconnected when no path exists between 2 vertices. So this here is a disconnected graph because not all of these vertices are connected with each other. It's impossible to reach here, so this is the reason why this graph is a disconnected graph. Alright, so now let's map out this concept in our code. Now what we want to do is we want to create a graph class that could be flexible enough to support directed, undirected, weighted, and unweighted graphs. Now the difference between a directed and undirected graph is that for directed graphs, which is, so this is an undirected disconnected graph because there's no link here and you can't reach here, so this is disconnected. The reason why it's undirected is the reason that both of these paths are like bidirectional. So over here Peter and Jordan is, Peter is friends to Jordan and also Jordan's friends to Peter, so this is bidirectional. So, and this is undirected. If it's directed, it would have arrows here, so it would point that Peter is only friends to Jordan, but Jordan doesn't like him back, and Jordan is friends to Cody and Cody doesn't like him back. So something like that is gonna be directed. In case of weighted graphs, you'd have weights on top of each. So I know it doesn't make sense over here, but if we had like bus stops and then their routes, it would have been easy to map out. But here if I say Peter and then Jordan, it takes like let's say 5, so it's something like this, and then we have over here we have, let's say 10, and over here let's say it's 12. So over here now we got weights on top of the edges, and these are just going to indicate the number or the expense that we're going to take here. So Peter I know it's not a good example. Like I said, we could have done with bus stops and routes, but here we're taking Peter is friends with Jordan, and I don't say 5 times. He likes him 5 times. This Jordan likes Cody 10 times, and Cody likes Peter 12 times. I'm not sure if that was a good example, but you got my point there. Something like that, with which associates the numbers as their expenses. With this in mind, we will create our graph with the following requirements. A vertex can store any data, so these circles. A vertex maintains a list of connections to other vertices, represented by a list of edge instances. So we're going to have a vertex, we're going to also have its list to connect other ones. So those are going to be called as these vertices, and they're going to be linked through the edges. So here we have Peter, but friends are Jordan and Cody, right? So we're going to have to put that in some kind of structure here. So it's going to be in a list of edges. So they're going to be represented by a list of edge instances. A vertex can add and remove edges going to another vertex. A graph stores all of its vertices represented by a list of vertex instances. So all of these vertices you see are just going to be stored in that graph structure. A graph knows if it is directed or undirected. Like I said, this is undirected, and if it had some kind of direction, it would have been directed. A graph can add and remove its own vertices. A graph can add and remove edges between stored vertices. With all of that out of the way, let's write the code. So to keep the concepts grounded in a real-world application, we'll build a transportation network of bus stops as we go. What I want to do first thing is actually look into my Vertex class. And because I know this is the circle which has the data, and it's also going to have the edges, so we're going to start from this one. Here we're going to go into this class Vertex here, and we're just going to create some instance variables. So the first thing that I am saying is the private string data. The second thing that comes to the mind is private array list, because we want to store the edges, right? So we say array list, we put the type of the array list here, so we're going to store edges. So it's an array list of edges, and we're going to call this as edges. Alright, so now we're done with that. Let's add a constructor here. We're going to say public, and we're going to say vertex. Here we're going to have a string, and we'll say input data, the data that the user will provide. And then for that we'll say the class variable is equal to the input parameter, and then we have this dot edges, which is the edges, and that would equal to the new array list. And here we want the edge, and we also want this. So here we instantiated the array list, which was this edges one. Now I know this is giving us problems because it's not allowing us to have this, so let's just import this, import java.util.arraylist, and the errors are gone. Here we have a vertex constructor that assigns the data with the input data, and also instantiates the edges list with a new array list of type edge. Now we got these vertices, right? Now we want to have a mechanism that will allow us to see these edges in live action, right? The other thing that I want to go through with this is that I'm going to create this as a directed graph. So there's going to be arrows here. A method called public void add edge. And over here we're going to add in the vertex and vertex and integer weight. Alright, so now that this is done and we just created this constructor for this, and we know the instance variables, let's move on to edge.java and create the instance variables for here. And then after that, we're gonna go back to this vertex.java and finish it up. One thing I want to make clear here is that I'm gonna create a directed graph. It's gonna be the ones that have the arrows. It's not gonna be the bidirectional ones, which could go both ways. It's just gonna be one stop to the other stop, right? It's a bus stop, so I don't want to go backwards. So in this case, it's just a directed graph. what we're going to do here is for the edge, like I said, it's just a line where you see in the graphical representation, but here I'm going to have to try to map it out in code. So I'm going to have the start vertex where it's coming from and where it's going to. So private vertex, and then we have the end. And over here we want to weight. We're also going to create this as a weighted graph that will have a cost for how much expense will it take to move from one place to another. Remember those numbers which were on top of those lines? So that's the weight here. So it's going to be a weighted graph as well. So I'm going to put a weight in here as well, and it's going to be called integer. And then when I say WIGHT, I'm going to put a integer weight, and notice I'm using integer and not int. It's the reason is that if I don't want to put anything, I could just type in null, and it would allow me to just like pass it in with no reason. And if I had an integer, I had to pass in something like -1. All right, so now over here we have a constructor, and I would say public edge, and let's create the constructor here. So the vertex, and I'll say the start vertex, so I'll call it as the start v, the vertex. And we have end vertex, so we have end v. We have the integer, and we call it as the input weight, WEIG. So there you go. So we got the start vertex, the end vertex, and the input weight that we're gonna ask the user for. So remember, this is just an edge that we are creating as users. So the class variable this.start will equal to the start vertex, which will be passed in as an input parameter. The same thing goes for the this.end, and it will equal to the end vertex, so we say end vertex. And we have the weight, so we say this.WEIGHT, and we equal it to the input WEIGHT. There you go. So now we're done with this, and let's just add in some other helper methods. So I'm going to be adding some helper methods along with this, and I'm just going to be copy pasting this. So here, these are the public vertex get start, and it's just going to return the start vertex. The public start vertex get end will return the end vertex of the the edge within the edge, and the integer get weight will just return the weight. Okay, so that was cool. Let's go back to the vertex.java file and just make some methods here as well. So for the vertex.java, remember, like I said, we wanted to create a function that will allow us to add some edges, right? We're adding a layer of abstraction here, and we're allowing the method over here will just add edges for us. So what I could do here is I could say a public, and I'd say void add ed. So add edge, so add edge. And if we want to add an edge to a vertex, so remember the current vertex is already in the context. So this will be the end vertex. So I'll just pass in the end vertex here, and also the weight if you want to give it some kind of weight. Remember, I said weight is optional. If you don't want to give it, it will be assigned as null. To do something like that, first of all, I'm going to have the call to this. I'm going to say this.edges, EDGES, because it exists an edges over here. And then there is a function that was called add for the array list, because edges is an array list. And we just add in a new EDGE, and we call in the constructor. So this constructor will pass in the this. It will get the edges end vertex, so it's going to be end vertex, and will also be the weight of the edge. So all of this will be mapped in here. So this is our add edge, and it's just gonna add some edges here. All right, so now we're gonna have to create the remove edge here. So we're gonna say public, and I'm gonna say void remove edge, and we have vertex, and we have end vertex, and over here we have the this dot edge edges dot remove, and the method for this is since it's edges is an array list, so remove if will allow us to add a predicate and remove all of the elements of this collection that satisfy the given predicate. Errors at runtime, exceptions thrown during iteration or by the predicate are relayed to the caller. Parameter here is a predicate, and here you can read it. It says filter a predicate which returns true for elements to be removed, and I'm going to add that predicate here. So over here I'm gonna add in, so I want to remove that vertex. So here I'm saying remove edge, right? And I'm in that vertex, so I'm in the vertex.java, and I want to remove that edge that was passed in as this one, so end vertex, right? I want to remove that edge from here. So I would say edges.remove if. Now I would say I'll remove that kind of edge, all right? And then we put this arrow bracket. So this is the arrow sign, and I would say edges, and then we say get end, because we're getting actually two things here. The edges are having two places. One is the first, and the second is the end. So you can see in the code over here, we have the start and the end. So the edge has two things, and what we want is the end. So that's why we are getting the second one, and that's going to be over there. So dot get end. And then we say dot equals. So we say if that equals to the vertex that we passed in here, I'm just going to copy that and paste it here. And if that equals, then just remove that from there. So we just need a semicolon here. If I could get a semicolon. All right. And that should solve our problem here. So it's just going to remove that end vertex that we passed in as an input parameter. It's going to look at this edges.remove if, and it's going to pass in this predicate logic that says find that edge which has the end vertex equal to the end vertex that was passed in. Pretty easy. Okay, so now we're gonna add in some other helper methods. I'm gonna copy paste this as well, so I'll just paste it here. So the first thing, let me just first zoom out and show you what I've done. Here we have this remove edge, and we have the add edge. Perfect. Over here we have this get data method. It's a string return type, and it's just gonna get the data for the vertex. Pretty easy, straightforward. And the array list edge, so this is the return type, and it's saying get edges, so it's just gonna return the edges that the certain vertex has. So it's just gonna return the list of it, this dot edges. All right, now over here we have a public void print boolean show weight. So over here we have this print method that's just gonna allow us to visualize our implementation, and it's just gonna show us how the graph is looking like inside of our structure. So it's pretty easy. You don't need to go into detail for this, and if you want to write this down, you can pause the video and start typing this in. We're done with the edge.java, and we're also done now with the vertex.java. In fact, I don't even need this main method here, so I'm just going to remove that here. And now we just have this. So the edge.java and the vertex.java are done. Let's go to the graph.java, the main thing, the main boss. So over here, we're just gonna add in the following things. Remember, like I said, a graph is a list of vertices. That's exactly what we want to do here. So I'm gonna say private, and I'm gonna say array list, and I'm gonna put in the type here. The type for this is vertex, because we're putting in vertices. And we're gonna pass in vertices, like this is the name. Now we also have our type, which I specified that there could be different kinds. And my graph will be a weighted graph, so I'm just gonna put in a is weighted boolean variable. I'm also gonna put is directed boolean variable, and this is just going to tell me if the graph is directed with arrows or if it's unidirectional or bidirectional. So that's the thing. Let's create the constructor for the graph, and we'll just say public graph, and then we'll just pass in boolean, and we'll say input is weighted. So the things that are passed in will be determined by the user, and boolean input is directed. So we're done with this, and here we're gonna have the this dot vertices, and we're gonna say new array list, and we're just gonna pass in. So over here we have graph, and then we have boolean input is weighted, and then we have input is directed. So like I said, we have to first initialize the vertices array list. So I'll just say new array list vertex, put the round brackets, and then the semicolon. This will initialize our vertex. This will initialize our vertices list, and for the weighted thing, so we can say is we weighted is equal to, and we say input is weighted. So weight for the other one, which is directed, so is directed is equal to input is directed. There you go. Cool. So now this is created, and yeah, I have to import the array list as well, so just import that as well. Now let's create some methods, and the important methods that we want to do here is that we want to create a method that will allow us to add add some vertices to our array list. And the name for that will be self-explanatory. It's called Vertex, and that's a return type, so it's going to be called add vertex. The data that will be passed in was as a string, and over here we'll say vertex, and we'll say new vertex, and over here we're just gonna create a new vertex here, so we'll say new vertex, and we'll pass in the data that was passed in, and over here we're gonna put that inside of our list, so we'll say this.vertices.add, and we put the new vertex semicolon, and then we have the return new vertex. Cool. So we're done with this. That's the add vertex method, and it just returns us the vertex, so we'll have to assign it to a variable in the main methods. So now we're gonna create the public void add edge method, and this will allow us to pass in the vertex 1, the vertex 2, so this is the start and the end vertex, and the integer weight. Like I said, I wanted to create a level of abstraction here, so I'm allowing our graph to have the add edge functionality as well. So over here it's pretty straightforward. If I said if the thing is weighted, then there's going to be no weight for this, because I passed in integer weight, and I'll have to first check the Boolean variable here. So if I say is weighted, not directed, but is weight. Now if the weighted was false, then so it says if weighted is false, right? So we'll just say the weight that was passed in will be assigned as null. All right, and if it's not false, meaning if the thing is weighted thing, so we'll say vertex 1 dot add edge, and over here we're actually adding the vertex 2, and here the weight will be passed in as well. And this is the add edge method that's from the vertex class here, so the vertex add edge, this one. Now over here we want to actually add in the other thing around as well, because we need bidirectional and unidirectional. So if it's undirected, then both, right? And if it's directed, then just one. So I'll say if it's not directed, then both. So this dot is directed. If it's not directed, then we'll have the vertex 2 dot add vertex, or yeah, so vertex 2 dot add edge. Here we're gonna add the edge, and we're gonna say vertex 1, and we're also gonna put in the weight over here as well. And there you go. Similar to how we created the add edge method, we now need to create the remove edge method. So let's go here a little down, and let's add the remove edge method. So we're just, like I said, I'm giving the power to the user to do all of this. So, and the user doesn't even have to know how the vertex Java or edge.java works. So that's the layer of abstraction that we're creating here. Remove edge, EDGE, and over here we're gonna pass in the vertex, and we'll say vertex. So to remove the edge, you'll need the vertex 1. You'll also need the vertex 2. Now to remove it, it's pretty simple. We say vertex 1 dot remove. This is the method that was there. So remove edge, and it takes another vertex. And we have the end vertex here, but we're just gonna pass in the vertex 2. And there you go. And then like I said, we have to check if it's not directed. If it's bidirectional, then we have to remove the other way around as well. So I'll say if this dot is directed. So if it's undirected, right? So if it's bidirectional, then we'll have to remove the other way around as well using vertex 2 dot remove edge, and we put in the vertex 1. Okay, so that was pretty much it with the remove edge. Now we have some other methods like remove vertex. So I'll just add in a remove vertex quickly over here, void remove vertex. And for the remove vertex, we have the vertex that's passed in as like this. And what we're gonna do is we're gonna say this dot vertices, which is the list that is existing here in this class, this instance variable, and we're gonna use the remove method that's provided by the array list, and we're just gonna remove the vertex that you just asked for, right? So that's just gonna be removed here. Now to save some time, I'm just pasting some helper methods that we also need here, so I'll just paste that in, and let's see how it looks like. So here we have the get vertices, the remove vertex. The get vertices method, it just returns the list. Is weighted, is directed. So that the last thing what we did was this one, which was remove the vertex, and then after that, this one is just a get vertices. It's just going to return the array list vertex. So the whatever the array list is, it's going to return all the vertices here inside of that current graph. Public boolean is weighted will return if the graph is weighted or not. And boolean is directed will return if it's directed or not. Public vertex get vertex by value, pass in a value, and it will loop through this for condition. It's going to go vertex. So you pass in a string value, and you're trying to look for that vertex for that kind of value. So let's say I have a stop in New Jersey. Let's say Jersey City. I'm looking for Jersey City stop for my bus, bus route. So in the bus service that I'm trying to map out here, let's say I have Jersey City passed in here. Now I'm going to have to look for that stop if it exists in this entire bus ecosystem. So if it exists in the bus routes, if there is any kind of bus stop that has the name Jersey City, and then it will be returned here. So over here I go for each loop, and it says over here the vertices list. So I'll say for every vertex v, if the value, so I'll use the get the data value, and this vertex, remember that I created get data over here somewhere, so it's supposed to be somewhere over here. There you go. It returns a data string, and if it equals to the value that was passed in as an input over here, then we'll return the v vertex, and then you'll have it as a vertex here. So perfect. And if it didn't exist, it will just return null. So that will help us know if the vertex exists here or not. And now over here, if you want to print it, so for vertex v in this dot vertices, v dot print, and we have is weighted. So the print method that we created here, this will allow us to see all of these vertices in action. Awesome. Now let's create the main deal here. Let's create some graph. Let's create the graph data structure, and let's try to map it out. And I'm gonna remember I said I'm gonna create a bus station, so I'm gonna say graph, and I'm gonna say bus network, and I'm gonna say new graph, and over here we're gonna pass in for the is weighted and for the directed thing. We're gonna pass in both true. So TRUE and TRUE. Now let me tell you why I did this. The first one was input is weighted. So it is weighted. There's going to be values associated to it. So for every edge, there's going to be some kind of distance. And the input is directed, meaning that there's going to be some kind of arrow, and it's not bidirectional. It's not two ways. It's just one way going forward. So bus network. And I'm going to use the add vertex method that we created here in this method. So it asks us for a string data, and we'll just say let's say Clifton, and here we have it semicolon. But remember that this add vertex method, if you go and see the method here, it's actually returning a vertex. So we're gonna have to store in some kind of variable. So let's store it in a vertex, and I'll call this as Clifton Station, and it equals to that. So there you go. And the same goes for the next one. So I'll say bus network dot add vertex, and we'll say vertex, and over here we'll have the next station, I'll just add a Cape May station. And let's have the vertex here as well. So vertex, and I'll say Cape May station. And just, there you go. So we created 2 stops. And I think that's enough for now. So now what we have to do is add the edges and the connections between them. So we use the, the add edge method. So we'll use bus network, and we'll say add edge. And to add edge, we have to put one station to the next. So we'll say Clifton station, and we'll say the Cape May station. So that's the connection, and we'll also have to put a weight. We'll have to put a weight as well. So I'm gonna say it takes 1,000 miles to reach there, and that's our weight. Cool. Now it's connected, and remember that I'm not putting it. So I'm just putting it one way, and it's just gonna connect it directed way. Here we have that. If I wanted to remove an edge, it would remove it using the same, but I'm just gonna say bus network dot remove edge and just pass in the same 2 things, not the weight that time. In this case, I just want to print it out and see how it looks like. So bus network dot print, and this is our method that is created here and actually calling all the vertices. So it's going to be printing it through here. Awesome. So let's run this baby up and see how it looks like. So I'm gonna command prompt here, and I'm gonna say Java C. The name of it is called graph.java. It compiled, and now after that, I'm just gonna paste here. So over here we have the direction from Clifton to Cape May, and it takes 1,000 miles. So that's exactly what we did here. Let me just minimize it quickly and go back here. And if I look over here, I actually created a direction from Clifton to Cape May, and it takes 1,000 miles. And I didn't do the other way around. Like I said, this was not undirected. It was directed because it was set to true. And here you can see that there's just one way from Clifton to Cape May to 1,000, and I can't go from Cape May back to Clifton. And if I want to do that, I could easily do that. I could just modify this. So input is weighted, that's set to true. If I just leave this as nothing, so by default it will consider that as false. So all right, so I'm just gonna have to if I add in false here, and that's just gonna make it undirected, so it's gonna go both ways around. And if I do this now, it's gonna go bidirectionally. So I'll say this, and then after that. So over here we have Clifton to Cape May 1,000, and Cape May back to Clifton 1,000. Using graphs to model complex networks is great, but graph search algorithms are another way graphs can be useful. A graph search algorithm can be used to traverse the entire graph data structure in search of a specific vertex value. There are 2 approaches to using a graph search to navigate a graph: DFS and BFS. DFS, or depth first search, follows every possible path to its conclusion. BFS, on the other hand, or breadth first search, expands the search from the point of origin to an ever-expanding circle of neighboring vertices. To track down what we visited, we add a list. This list will be very crucial because it prevents the search from returning to the same vertex multiple times. This is especially important for cyclical graphs, where you could otherwise end up in an infinite loop, and we've seen this in our previous videos. So you might be wondering, how does one compute the runtime of graph search algorithms? In an upper bound scenario, we would examine every vertex and edge. As a result, the big O runtime for depth first and breadth first search is O of vertices plus edges. So you have the O and you have bracket vertices plus edges. Now here's a question. What if you don't need to find a path, but you do need to find a list of all the values in a graph? What should be the solution there? Well, it turns out that in addition to path finding, depth first search is pretty adept at organizing vertices or vertex values with a clear order of visitation from beginning to end. So you could use depth first search to find a path, like instead of path finding, but you could organize and show the layout of the complete graph structure using depth first search. There are 3 main traversal orders that you'll come across for graph traversal: pre-order, post-order, and reverse post order, also known as topological sort. Pre-order, in which each vertex is added to the visited list and added to the output list before getting added to the stack. So that's just one thing to remember here. In post order, in which each vertex is added to the visited list and added to the output list after it is popped off of the stack. And then reverse post order, which is also known as topological sort, which returns an output list that is exactly the reverse of the post order list. So post order and reverse post order are just like the opposites of each other. Here I have a cool graphical representation of a graph. Take a look at this directed graph structure that I've depicted here. Let's say that we want a list of all vertex values starting with 1 in the order that they are added to the stack. Now a pre-order DFS traversal would come in handy. Now over here we'd assume that the algorithm prefers visiting things in numerical order if there is a choice. So our target value is 1, and normally you would get a target value from the program. So our target value is 1 here, so we're starting with 1. We'll go with 1, so this is the first thing that's visited. This is also going to be on top of the stack. So over here, if we have a choice, we're going to prefer visiting the minimum number. So over here we have 3 and 4. We're going to check 3, so we're going to go and visit 3, and we're also going to put it on top of the stack over here. After that, we see that there's 4 and 2, so we're going to look at the smaller number and we're gonna visit it. So 2 is going to be over here, 2 is also going to be over here, and then we're also going to check for 5. So because it's 5 and there's no other option, so we're going to have to check 5. We'll put it on the stack as 5 over here, and the visited will go over here as well. Now the important part came, and you could see that there's nothing after this, so we'll have to pop this thing out of the stack. So we're gonna have to, I'll just pop it out like this, and now we'll check 2. So 2 still has nothing with it, so we'll pop that out as well, and then we'll check 3. So 3 has something, so it has thing that was not visited, and it was 4, and it's not in the visited set, so we're gonna add that 4 over there. So just add 4 to the top of the stack here, and we're gonna add 4 here as well. Now we're gonna check for the 4, and we're gonna see, well, the 4 doesn't have anything, so we're gonna pop that out of the stack as well. And then after that we have 3, so we're looking at for 3 something, any number that is already that is not visited. So everything is visited, 4 and 2 are visited, so we're gonna remove 3. We're gonna look at 1, and if there's anything that is not visited, we'll have to check, but there's nothing, everything is visited, 3 and 4 are there, so we'll remove that. So this is how our list will appear: 1, 3, 2, 5, 4. So this is the pre-order DFS traversal. All right, so like I said, that pre-order is that kind of order in which each vertex is added to the visited list and added to the output list before getting added to the stack. So this was our pre-order traversal. Now we want to look at post-order traversal, in which each vertex is added to the visited list and added to the output list after it is popped off of the stack. So if we take a look at the post-order traversal, we'll go like this. So for the first thing, it's 1, so we're just going to look at 1. We're not going to add it to the list or anything yet. Then we're going to look at the smaller number, which is 3. Then we're going to look at something even smaller than that, which is 2. Then we're going to look at something, and then we have 5. So there you go, the last number came, so it's going to go like this, 5. And then after that, it's going to go and see the 2, because it's going to be popped off as well. So 5, 2. And then we're going to look at 3. So 3 actually has something for this, so we're going to have to add 4. And then we have nothing over here, so 4. And then we have back to 3. So back to 3, and then we have the last one, which is 1. So this is our post-order traversal. This is how it's going to appear. And the reverse post-order, which is also known as the topological sort, will return an output list that is exactly the reverse of the post-order list. So this is the post-order traversal, and the exact opposite of this is 1, 3, 4, 2, and then 5. So this here is the reverse post order, also known as the topological sort, and these are just different ways to traverse the graph. The most common was the first one, which was pre-order, and that's the default thing. And it's easy for us to just get a full overview of the graph like that. All right, so let's have a conceptual overview of how the depth first search DFS is going to work. So let's suppose we have our target value as 1. So we're going to go and visit 1 here, and we're also going to put it on the stack. So this is the top of the stack. Then we'll have to look at the number that is smaller from the choice over here. We got 3 and 4. We're looking at a smaller number, and we'll put 3 on top of the stack here, and we'll put it as our visited set as well. So we have 3, and then after that we look at the smaller number from these two, and the 2 is the smaller number, so we'll put it in the visited set, and we'll also put in the DFS stack. So we'll put it up on the top over here. And now we can see that 5 is the only option, so we'll have to use 5 here as the visited, and then we'll have to put 5 here on the top of the stack as well. Since there's nothing over here on the there's nothing after the 5, so we're gonna have to pop this out. So to do this, we're gonna have to just select this number and just pop it out. And now we're gonna look at 2, so there's nothing with 2 as well, so we're gonna have to pop this out. 3 has some unvisited vertex, which is this 4 one, because this is not in the set over there, so we're just gonna have to use this now. So we're gonna use 4, and we're gonna put it over here. So 4 is gonna be over here, and 4 will be on top of the stack as well. Now we look at 4, because this is our current vertex, and there's nothing over here that's unvisited, so we're gonna have to pop this out again. So let's just pop it out. So there you go. So this is popped out, and now we look at 3. There's nothing unvisited, so we'll just pop this out. Look at 1, and there's nothing unvisited, so we'll just pop that out. Once the stack is complete from here, so it's empty, we'll have a list over here, 1 3 2 5 4, and this is a list of all of the vertices inside of this entire graph. So we have 1 3 2 5 and 4. This was our DFS, depth first search. Now let's write the code for this. So here I have a class graph traverser, and it has a main method, and also I have a sample graph that I've created earlier, and it just contains some vertices, and yeah, it just has a method here that says get starting vertex, and we'll get the first vertex here from the graph. Now our job here is to write the code for a depth first traversal. Traversals are extremely useful when trying to find a specific value or path in a graph. We'll start with the depth first traversal method for recursively traversing a directed graph. To summarize, depth first traversals iterate down each vertex, one neighbor at a time. In this video, I'll focus on traversing the entire length of a single path and printing the data value of each vertex. Now in testgraph.java, I've created a sample graph for us to test the traversals against. This is all linked to my last video about graphs. So we created a graph here, and we have this input is weighted as false and is directed as true. So there's no weight, but it's directed, meaning it has directions, right? And we have a vertex start node, and we have testgraph.addVertex, and we have the name. So these are the names of our vertices, and yeah, so there are all these vertices here. Now I have all of these vertices that I added, and then I created these variables to associate to them. And then after that, what we did is add edges, so connections were done. After that, we created a cycle here as well. And this is not exactly the same graph that I've made in the diagram. So what I have here in the diagram was just simple so that you could easily understand how DFS works. But here I just created a complex one so that we could test out cycles as well and other things. After that, we have this graph traverser.java. To keep things simple, I created a separate graph traverser utility class in graph traverser.java, and I'll implement the traversal iterator as a static method here. Now I've seen implementations in which they created the iterator inside of the graph class. So now let's start writing the code here in the graph traverser.java utility class. We're gonna first of all, let's just add a method that is for the depth first traversal. So we say public, and we say static, because it's a static method, and void, and we're gonna say depth first, because we're using a static method here because this is a utility class. So depth first traversal, and here I'm just gonna pass in the vertex to start with. So one, I need the start vertex, and also I need a list of all the visited vertices for this start one. So that will be called as an array list, and I'm gonna put in the vertex type here, and we're also going to put in the name as visited, and then we have vertices. Cool. So now we're done with this. Let's add in the things here. First, let's just print out the value of our start data. So we have a system.out.println, and we say start.get data. So you might be asking, where do I get this get data from? So I already have vertex.java included here, and I've created this in my previous video. So we have a get data method, and it just returns the string data. Now we're gonna have to iterate through this vertex, and we're gonna check its edges. So all of the edges for this start vertex. So we could use an edge edge of e. So for all the edges e in the start dot get edges. So this is also a method inside of the vertex class. So over here I'm saying for every edge inside of the start edges. So this means all of those neighbors that are connected. All right, so we have to get the neighbor vertex. To get that, we got to use e.get end, and this will give us a vertex. You can see that returned gave us a vertex, and we can save it as a vertex neighbor, neighbor. Now, one thing to note here is that this e is an edge, and the get end is from the edge class. So this is also here. So get end is going to be somewhere over here. There you go, and it returns the vertex end from there. So it's just pretty simple. This one, the end vertex. Now, right after this, I'm gonna have a conditional here, and I'm gonna check if my visited vertices does not contain this thing. So I'm gonna add it inside. So now we can know, and we could mark that we already visited or not. To keep track if we visited vertices or not, we're gonna add this conditional. So if we're gonna use visited vertices, and then we say dot contains. And then we have the neighbor, and I say if that contains inside of the visited vertices, because you know that the visited vertices was passed here, and I'm saying if it's not inside of the visited vertices, then we want to add it. So we'll just put a negation here, and let's also quickly add this import. So just over here and quick fix import the array list as well on top. Okay, cool. Now over here in this inside the conditional, I'm gonna add in the visited vertices, and I'm gonna say dot add, and I'm gonna add in the neighbor vertex here. So I'm gonna say neighbor. Since our visited vertices holds vertices, and we could easily add a vertex here. The really important recursive call here is that we're gonna do a recursive call that will go to the graph traversal again. So you're gonna call the graph traversal, which is this current class, and we're gonna call the method, which is def first traversal. And now it's requiring us a start and visited. So the visited vertices will be the same thing, but now we're gonna go with the neighbor. So neighbor. Okay, so we're done with that, and the conditional is done, and here is the for each loop, and it's going to iterate through all of the edges for our start vertex, and it's going to go until it's done. So that's pretty much it with our depth first traversal. We could test it out in our main method. We're going to create a test graph, and we're going to say test, and what we're going to say is new test graph. Okay, so where am I creating this from? This is actually from this place, and this is just creating a test graph. Remember, like I said, it created this whenever this is a public test graph constructor, and in the constructor is just doing all of the work for us. So normally we would put this in a main method, but we're putting this in a constructor, so it's creating a gigantic, ginormous kind of graph with so many vertices. So v1, v2, v11, v12, all of these. So 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices, and they're connected edges. And what's it going to do is it's going to show us through this. So we're just going to create it here, and we're going to pass it in. So before that, we actually need the starting vertex of our test graph as well, and we had created this handy method here, which was get starting vertex, which returns us the first vertex in our graph. So we could use test, and then we say get starting vertex, and this would just give us the starting vertex, and we could save it somewhere inside because it this actually returns a vertex type. So we could say vertex, and then we say starting vertex. So we'd say starting vertex, and we'll just equal it. Okay, cool. So now that it's equal, now we could add in the visited vertices. So now let's add the visited vertices list. So array list, and I'll put the type as a vertex, and I'll call this as visited vertices. So visited vertices, and here we're gonna pass in a new array list, and here we're gonna just instantiate it, so like that, and just semicolon at the end. So we created a visited vertices array list as well, and we're gonna add in the starting vertex because it's already visited, so we're just gonna add it before all of the operations, and we'll just add in starting vertex here. Cool. Now when it's done, we're done with this initial thing. Now we can finally call our depth first traversal. So this thing, and it's really easy. It's the name of the graph, traverser dot depth first traversal, and it's asking us for the start vertex. So we'll say starting vertex and the visited vertices, and this should print it out. So let's go into this place, which is right here, and command prompt it here. And let's go down and let's say Java C, and we say graph traverser dot Java, and now let's just run it. So Java graph traverser. So here we have the way how this will work. That's pretty dope. Now it's time to focus on breadth first traversal. As a reminder, the breadth first traversal iterates through the graph in layers. It goes down one layer, which comprises the start vertex's direct neighbors. Then it proceeds down to the next layer, which consists of all the vertices that are neighbors of the vertices in the previous layer. And for this example, I'll focus on traversing down one layer, and then take a similar approach as we did with the depth first traversal by keeping an array of visited vertices to prevent us from iterating through the same vertices over and over. However, we will iterate through all of the direct neighbor vertices instead of iterating down the neighbor's first edge, like we did in depth first traversal. We will also use a queue to traverse through the graph instead of recursion to explore the different ways we can implement the traverse. I'll reuse the same test graph that was used in the depth first traversal implementation. All right, so what I have is a directed graph, and I'm gonna have to apply breadth first traversal. So what I'm gonna do is I'm gonna get my target value. Suppose we have it as 1, starting value, and I'm just gonna put it in the visited, and I'm also gonna put it in our BFS queue. We're gonna look at our adjacent vertices and see the smaller number. So here we have 3, and we're gonna choose that as the first one. So we're gonna say 3 as our visited, and we're also going to put 3 here as well. Now that we've done that, we look at the other adjacent one, which is 4, and we're going to add that in our visited set, and we're also going to add it here in our queue. Now that we've exhausted our current vertex, since there are no more unvisited vertices, so we're going to have to remove this 1 from our queue. So we're going to remove this 1, and now 3 will be our new current vertex, and we'll look at the adjacent ones here. So we have 2 and 4, but 2 is smaller, so we're going to choose 2 first, and here we have 2 in the visited and 2 in the queue. Now we also have 4, but 4 is already visited here, so we're not going to look at that. Now that we've done this, we're going to have to since 3 is exhausted now, we're going to have to remove that as well. So we're going to dequeue it, and we're going to now look at 4. Now 4 is over here, and there's nothing that we could visit, so we're going to have to remove this as well. So we'll remove 4, and after that we could see 2 is now our current vertex, and 2 has a neighboring vertex, which is 5. So we'll put 5 here, and it's the only neighboring vertex, so we'll just put the BFS queue over here. So now that we've exhausted 2, we'll remove it from there as well. And 5 is also nothing, so there's nothing with 5 as well, so that's completely exhausted as well. So here we have completely visited the entire graph using breadth first search: 1, 3, 4, 2, and 5. Awesome. Now let's write the code for this. So I'm going to the same file where I created my depth first search, and I'm going to add my breadth first search right after this. So this is my depth first search, and right after this I'm going to create my breadth first search. So I'm going to say public, and we're also going to make this as a static method, since this is a utility class, breadth, FIRST, and then SE search. So depth first search, breadth first search, add in the vertex start, just like that, and also the array list, which is the vertex, and this is going to be called the visited vertices, just like what we did up on the top for our depth first traversal. Now, since you saw the graphical implementation there, I used a queue, so I'm going to create a queue here as well. So queue, and I'll call it visit queue, and here we're going to equal it to new queue, so QUEUE, and we're just going to put that as well. Now you might be asking, where is the queue coming from? Well, I actually have the queue file here as well. So this is the queue.java file, and we've created queues before, but I actually modified it here a little bit. So the same exact queue that we've created in our video series, but I just modified it a little bit just to add vertex as the data now instead of a string or some kind of integer. So removing that, and now let's just go here. And over here now we created our queue. It's called our visit queue, and we're gonna have the visit queue dot enqueue, the first thing, which is the start, which was passed in as the input parameter, and that's the vertex there. Now we're adding a while loop, and this is going to go until the visit queue is not empty. So I'll say visit queue, because this is a queue, it has this method which is empty, and I've created that one. So I'll say if it's not empty, we're going to go inside of this visit queue and keep doing those removing queue things, and traversing and using breadth first search there. So for that, let's just get something down and actually dequeue the element in the queue. So we could say visit queue dot dequeue, and here we have a vertex that we have to dequeue, so we'll put it inside of a current variable. So I'll say current. All right, so now that it's in current, we could print out the value here as well. So just say system dot out dot print ln, and then we say current dot data, and there's a get data method that was in the vertex class. So there you go, it's working there. Now that we're using a for each loop to go through each of the edges inside of this current vertex, because that's what I showed you in the graphical implementation. Now I'm just mapping all of that entire explanation down in code. So I'm saying edge for every edge of the current vertex. So it's a current dot get edges, which is returning an array list of edges. And what we could do here is that, so now we're going to get the neighboring vertex of the current vertex. To do that, we could easily get it from e.getEnd, and that returns us a vertex. That's our neighboring vertex, and we pass it in to this vertex variable, and we'll call it as neighbor. And over here we'll apply a conditional, and we'll say if the now since I'm using a visited vertices array list over here in my input parameter that checks if something is not repeated twice, so I'm saying if it's not existing, so I'll say if visited vertices dot contains, and the neighbor thing, NEIGHBOR. So I'm saying if it does not contain it, then you should add it. So I'm saying if it does not contain that neighbor vertex, then you should add it. So we'll say visited vertices dot add, and so visited vertices dot add, and then we'll add in the neighbor vertex. Perfect. And then the last thing that we could do here, because we created this visit queue, and we'll enqueue this inside of our visit queue. So we'll just say visit queue dot enqueue which is this, and we'll put in a vertex data. So we'll put in that vertex, which is the neighbor, NEIGHBOR. So this will be inside of our visit queue, which is this queue, and it just currently had only the start. But once you get the edge of the neighboring vertex, you also pass that inside of the visit queue. So that will be now the current vertex, and it will go until there's a dead end, and then we'll just remove from the in queue, and then so once it's exhausted, like you see over here in this while loop, so it's just going to say until it's empty, not empty. So it's just going to keep going, and once it's exhausted, like you can see over here, DQ, so it'll just see the other vertices that are there to traverse. Now let's go down in the main method and just have everything over here set like this. So just pause the video and type along. And over here for the starting vertex, test.starting vertex, here we have a array list vertex, visited vertices, the same thing. And this is the same exact thing. So instead of depth first traversal, we're going to say breadth first traversal. And the rest is history. And compiling it and running it. Let me just label them as well. So system.out.println, or we could just have a line here. So print, and then we say DFS. I'll say BFS. Run this. So here you go, the difference between the two of the traversal techniques. Here we have DFS, at the other side we have BFS. So we have over here 0, 1, 1, and something like that, and then we have 2 over here. So something is going on differently, but if you look at the total numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So the total number should be 10. There's 10 over here and there's 10 over here. And if we look at the test graph.java here, so the start node 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Awesome. So that was it. That was my code for depth first traversal.
Welcome to another video. Today we're going to be talking about Dijkstra's algorithm, a very important algorithm in the computer science world. Finding the shortest distance between vertices is one of the most common applications of graph searches. Finding this distance has a number of applications, including determining the best route to a destination and transferring data over a computer network. Consider the graph. Finding the shortest path between vertex A to vertex E may appear simple in your mind, but telling a computer how to do so is a bit more difficult. Fortunately, there is an algorithm that computes the shortest distance between any two vertices in a graph. This is known as Dijkstra's algorithm. Now, let's look at the conceptual overview of how the Dijkstra's algorithm is going to work. We're going to start with the starting vertex, and you can see that the start is pointing to A. So this is my target vertex. Here I have a distances queue, and I also have this unvisited, which is in the bottom. Now, I'm going to look at the first step here in this algorithm, and the first step is to pop off the minimum distance of the unvisited vertices. Now you can see over here the minimum distance here is 0, and these rest are all set to infinity, meaning that the distance from A to itself is 0, and the distance from A to any of one of these vertices is infinity for now. And if we look at the minimum distance right now, it's 0. So we're going to pop this off. So we're going to pop it off from here, and then we're gonna look at the adjacent vertices corresponding to this first vertex. So you can see over here, so from A to B, the distance is 4. Now if you compare this with the original distance, which is infinity, now 4 is less than infinity, so we could replace this infinity with 4. Since we replace that, now we could also go and check the next corresponding distance. Now A to C has a weight of 2. Now you could see that 2 is less than the infinity. Now we could also replace this infinity with 2. Now we're done with that, and this is our first iteration of the algorithm. Now we're gonna go to the next iteration. So now we're gonna pop off the minimum distance of the unvisited vertices, and you can see for now we could see that 2, which is for C, is the minimum vertices. We're gonna pop that out from here. and we're going to start with C. So you can see C has C only has one neighbor, and that is E, and the distance from C to E is 1, and you have to look at the distance from A to C too. So the A to C was 2, and from C to E was 1. The total distance from A to E is 3. So 2 plus 1 is 3. So what we're gonna do here is we're gonna make from A to E as 3, and then we're gonna look at the E portion, and we can see that 3 is less than infinity, so we're gonna replace this infinity with 3. Now, since there's no more neighbors left, we're going to do the next iteration for this algorithm. C has no more neighbors. So now we're going to pop off the minimum distance of the unvisited vertices. You can see now that the minimum distance is 3. So it's in E. So we're going to pop this off, and we're going to go to E. And look at the neighbors for E. So E has only one neighbor, and that is D. The weight for that is 5. The distance will be 3 plus 5, which is 8. And 8 is less than infinity, so we could replace this infinity with 8. Now that we have replaced that, we could also see that there's no more corresponding vertices, so we could stop here and do the next iteration for the algorithm. Now we're going to pop off the minimum distance of the unvisited vertices. So you can see that the minimum distance is B. So we're going to pop this off. And over here, we're going to look at the corresponding neighbors. Now B has 1, 2, and 3 corresponding neighbors. We're going to start with the first one, which is C. So B to C is 1. And now you can see that from A to B, which was already existing, was 4. And from there to C, it's 1, so 5. So from A to C will be 5. And if we look at the C, it already exists here, and you can see 5 is greater than 2, so we're not going to change this value. Then we're going to look at the distance from B to E, and that's 3. So from A to B, it's 4, and from there to E, it's 7. So if we look at the distance from A to E, that should be 7, and that is greater than the value that we already have here, so we're not going to change that at all either. Now we're going to look at the last and final neighbor of B, and that is D. Now if we look at the weight, this is 2, and the distance from here was 4, 2, so it's going to be from A to B it's 4, and from B to D it's going to be 2. So the total distance here from A to D will be 6, and if we look at the distance over here, that is actually lesser than what we have existing. So we could replace this 8 with 6, and that now will be the end of our iteration, and now we'll go to the next iteration of our algorithm. Now we're going to try to pop off the minimum distance of the unvisited vertices, since we only have one vertices left, which is D, and we look at the minimum distance here, and that is the minimum distance. Everything has been visited, so that's D. So we're going to pop it off, and we try to look at any neighbors for D, but there's nothing. So that's the end of our algorithm there, and that's how Dijkstra's algorithm is implemented. So you went over there and saw all of the possible distances. So from A to itself, the minimum distance is 0. From A to B, the minimum distance is 4 till here. From A to C, the minimum distance is 2 right here. From A to D, the minimum distance is 6, so 4 to till here. And from A to E, the minimum distance is 3. So A to E is the minimum distance is 3. So that sums up our Dijkstra's algorithm conceptual overview. Now we're gonna start writing the code for this. But before getting on to the code, let's think of what we should add in, or what objects and what structures should we create. Looking into this algorithm, we're gonna instantiate a dictionary that will eventually map vertices to their distance from the start vertex. So like you can see over here, we're going to put that in a dictionary. A quick recap before we start the code for this. Dijkstra's algorithm finds all of the shortest distances between a starting vertex and the remaining vertices in a graph. The algorithm operates by keeping track of all distances and updating them as it performs a breadth-first search. Dijkstra's algorithm is implemented in O of E plus V of log of V, and E means edges and V means vertices. We will first implement the algorithm to find the shortest distance to every vertex. So let's go for the code, and all of the conceptual overview that I gave, now I'm going to try to map this out in code. So here I have imported java.util.asterisk, meaning I'm importing everything that's available in the utility package, and over here that you can see is public class Dijkstra, and there I have a main method. Here I have a main method which is actually creating a test graph, and the weighted and directed properties are set to true, and we also add these vertices here, so A, B, C, D, E, F, G, and we also add their connections to each other, so those are done. So what we mainly have here is a test graph in our main method to test the output of the method of what we're going to create in this video. So we're going to try to create that method, which is called Dijkstra's. So for that, we're going to have the public, and we're going to say static dictionary, and we put in this. So we're going to return an array of dictionaries, and I'll tell you why we're doing this in just a sec. So here we have the name of the algorithm, Dijkstra, and we're going to tell the parameter to add in these two values. First thing is to have the graph, so graph, and we call that as G. We also need to pass in a vertex, and that one will be called as starting vertex. So we're done with these two input parameters. Now we're going to create two dictionary objects here, and one will be used for the distances queue, the other one will be used to keep track of your previous vertex, and this is very crucial in this algorithm. So to make a dictionary, and a dictionary is just a base of key value pairs. We have a string, which is the key, and integer as the value, and we call this as distances, and we create a new hash table, and we put in these angle brackets and the round bracket, and then we semicolon at the end. So that's the distances queue. Now we also need another hash table, and this one will be for the previous. So we add this as well, and for this we're not going to have the integer as the value but the vertex. This is going to store the data and the also value that it exists. So like I was doing it over there in the diagram, this A, and it maps out to 0, and this B, that maps out to 4. So the string is the letter and the value is going to be the integer. And for the second dictionary, which is previous, it's going to keep track of the previous vertex. So that will have a string, which is the current vertex, and vertex will be the previous vertex. Now we also need to add in a priority queue. So I have added some files here, and this is one that's called queueObject.java. This is actually a class that implements the comparable queue object, and you can see that it has the vertex and the priority as class variables, and you can see the constructor is actually creating this object, and it's overriding the compared to method with some priority base. So if it's equal in priority to the input parameter, we just return 0. If the class variable priority is greater than the priority that was passed in, then we will return 1, else we will return -1. So this is just a file, and it's just a fancy queue. It's just known as a priority queue. The main difference between this queue and the priority queue is that this will look at the smallest possible value, and it will allow us to pop that one off. So like what we're trying to do here, we were trying to look at the minimum value, and we were trying to pop that off. That exact implementation, this priority queue, will do it for us without writing extra code. So that's one of the biggest benefits for using that. So let's add the priority queue, and this is the priority queue. So priority queue, and we're gonna add in the queue object here. So queue, and we're gonna say object that we created, and then we could add the name for that as queue is equal to. Now we're gonna add in the new, and we'll say priority queue, and here we're just gonna add in the queue object once more. queue object, and then a semicolon at the end. Perfect. So this is our priority queue created, and let me just add in the same exact line. So just after that, now you might be asking, well, the priority queue is actually empty right now. We got to queue something inside. Now the thing that we're going to queue inside for the first thing is the starting vertex, since we know the distance for that is 0 to itself. So we're just going to queue that up in here. So we say queue.add, and here we're just going to say new queue object, and we're going to pass in the vertex v and the int p, which is the priority. The vertex v is just going to be the starting vertex, and the priority for this would be 0. Awesome. Now we're going to try to iterate through this entire graph that was passed in as an input parameter, and we're going to try to iterate through and try to find all the vertices here. So we can use a for each loop for this purpose, and we can say for every vertex v, and we can say for every vertex v in the g.get vertices, and this is returning an array list of vertex, and you're just doing this really easily. And this is also added here, so I have a graph.java file, and this is also added, so that's why I'm able to get the method get vertices. So this is get vertices, and it should be over here somewhere. Get vertices. So this is the get vertices method, and I'm also adding this edge.java as well as this vertex.java. You could look at my older videos, and from there I'm actually using all of those classes that I've created in the graph.java, the vertex.java, and the edge.java were all done in a single video, which was called graphs in Java. So watch that video. And for this queue object, I'm just gonna let you see this code for it. Now you could just pause the video and copy this, and once you have all of these, we could go back here in the Dijkstra.java, and we're just going to iterate through the vertices which are in this graph, which was passed in as an input parameter. Now we're going to have to iterate through this, and we're going to actually update our distances, which was over here. So we're going to actually have to update our distances and previous dictionaries. So we're going to try to add all these vertices from this graph to this distances and previous dictionaries. We could do, first of all, we don't want the starting vertex to have a maximum integer of max value, because we know that the starting vertex to itself is 0. So we're going to give a condition here and say if the vertex you get is the starting vertex, and this is just going to work. So we're going to say if that one is the starting vertex, we don't want that. So if it's not, right, so we want to update the distances, and we're going to have to add input. This is a method available in the dictionary, and this allows us to add a key and value pair. So the string is the key and the value is the integer. So what we could do here is for the string we could say v, which is the vertex, and we say dot get, so we could say get data, and that would return a string here, and this is also added in the vertex.java, so that's why it's working here. And for the integer, we could just add in the maximum, or we want to use the infinity symbol, right? Well, you could use integer.max value. This would give us the maximum value for the integer in Java, and that will be stored inside of the value pair. So key values are done. And for the other case where we have the previous dictionary, so we'll say we'll say previous.put, and for this second dictionary we'll also have a key value pair, but the value is a vertex. So the key is going to be the get data, the same thing, but for the value in this case will be the previous vertex, so that we could keep track of this. So we're just going to add in a vertex that will be set to null for now, and then after that we're going to update it inside of our code. So right now just set everything to null, including the starting vertex. Alright, so right after this we needed to add in the starting vertex here in our distances because we don't have it. So to do that, we'll just add in the distances again, and we'll say put. And now we want to add in the key value pair for that. And for this, add in the starting vertex, and we actually need the value for this, and we could say get data, and that will give us the string data. And for the value, I'm not going to give the maximum value. We're not going to give infinity, because if we look at this code over here, initially it was set to 0. So we want to just set it to 0 here. I'll put it there. And there you go. So we created this entire thing, what you can see over here. So you can see this entire thing that we've created, which has A set to 0, and the rest are all set to the infinity or the max value. Now, let's go back. And we're gonna actually do the second step for this algorithm. Now it's the fun part. We're gonna have to iterate through the while loop, and we're gonna check if the queue is not empty. So we say QUEUE. This is our priority queue, and we say the size method here. And if we say if that size is not equal to 0, we're gonna do some operations inside of this queue. First of all, we're gonna get the current vertex here, and that is pretty simple. Queue.poll retrieves and removes the head of this queue, or returns null if this queue is empty. So we're gonna actually remove an item from the queue using this method, and we want the vertex here. So we just say the vertex. Because we had this over here as this queue object, we wanted the vertex here. So we're removing that from the priority queue. So the first thing will just be the starting vertex, and that was added in our queue. So this was added over here. Queue.add new object starting vertex with the value as 0. So that was 0 was actually its value to itself. So this is now set to current, and we removed it from the queue. Perfect. Now we're going to iterate through this current variable, which is the starting vertex. So we're going to look at all of the edges, or the neighbors for here. So we say for every edge E, and we say mapping out to the current get edges, which is the array list returning of edges. So for every edges or every neighbors inside of this current, so every edge, an edge contains vertices, remember? So we're actually going to first look at the value of what the edge is giving us. Remember, like I did in this first one, that we were looking at the values, and we also judging inside of our distances. So we looked at, let's say for the distance to D, we had some already included distance was 2, 1, 5, which was 8. So that was already passed in. But we also want to keep track of the newer one. So this is like 4, 2, which is 6. And now this is an alternative one. We have to add that somewhere. And then we have to judge something, like if it's less than the original one, then we could replace it. So we want to have an alternative, and we want to also have the original. So for the alternative case, we'll add in an integer. And I'll say alternative. And I could add the distances here. So distances, and this is the distances dictionary, and I'll get the current get data, and that is the string. And we also want the plus to the get weight. So we're gonna get the weight as the int. So this is the distance from the current distance of the variable and the edge distance. So what this means is whatever the distance is existing for this current get data, the starting vertex is actually 0 to the distance where it's leading to with its vertex. So the edge where it's leading to with its edge. This makes sense because this is 0 to itself, but if we're moving forward, we have an edge with it, and we have some weight. So we're adding that weight as well. So get weight. That's the alternative. And we also need a reference to our string neighbor variable. So we could have that as NEIGHBOR. So this is our neighbor value. And we just have to keep it inside. So we could say E.getEnd. So this is the end vertex. And we want the value for this. So we have E.end and we have get data. So over here it's pretty simple. We have a neighbor value, and we want to have the edge vertex. So we want to have the edge, and we want to get the end. So we're going to get the vertex through this. And to get the data, we just say this. So we're going to get the vertex through this get end, and we're going to get the data. So that string is actually stored in the neighbor value. Now that the string is stored, we could use a conditional here to check if the alternative value is lesser than the original value. So what we could do here is pretty simple. We'll say alternative is less than the distances, and we want the dictionary. So this is the distances.get, and if we want to get the value for this, we could just use the neighbor value. So that's why I stored it over there, so that we could get the value of their neighbor value. The alternative value is less than our neighbor value. So what we're going to do is that neighbor value is actually the original distance that was stored inside of our distances object, which is on top. So over here we have distances. If that is possible, we're just trying to override it then. So we're going to say distances.put, and we're going to get the neighbor value. So that exact neighbor value, but we're going to change the value to the alternative. So we're going to get the key and the value. So this is the string neighbor value, and then the integer will be now the alternative distance. Also, we're going to have to modify our previous. So we're going to have to add in the neighbor value as well. So for the neighbor value, we actually need the previous reference, and the previous reference will now be for our current instance. But the current one, which is actually starting vertex, will be the previous vertex for our neighbor value, which is the current one over here. So it's just gonna keep iterating this and updating our previous reference. And the last thing what we want to do is we want to add the neighboring value to our queue. New queue EUE object, and we have to add in the vertex here. So we're going to say e.getEnd. So that's just going to give us the vertex here. And to get the priority, we could say the distances structure dot get, and to get the value, I'm just going to add in neighbor value, and that will give us the value. So this is neighbor value is the key, and it will give us the value which is associated to this key, and that will be updated to our queue, and that's going to be our priority. So that will be added, and once it's done, we're actually going to break out from this for loop when all of these edges are done, and that will be updated. And after that, until the while size is not less than 0. So this is just the line that will pop off the minimum distance of the unvisited vertex, and the rest is history over here. What you saw all in the conceptual overview, everything is happening and adjusting. And the right at the end, so when the while loop breaks, so the Dijkstra is requiring us to return a dictionary array, right? So we want to return that. So over here, right after the while loop, we could return a new dictionary, and so over here we're going to return a new dictionary, and we're going to get this square bracket over here, which is the array for this dictionary, and this is the array of the dictionary, and we want to pass in the distances with the previous structure here. This is the return statement. We're going to return a new dictionary, and it will have the distances and the previous dictionaries. So we'll have both the distances and previous dictionaries inside of this dictionary array, which is returning here in our function. So we can hear that dictionary array is returning. So this is the return statement at the end. And yeah, so that was pretty much it with this function. This is minimizing it so that you can see the entire thing. So this is the entire method for Dijkstra. Now we also have this helper method on this bottom, so I'm just going to paste this in. This is called the Dijkstra result printer method, and what it accepts is an array of dictionaries. Wow, how convenient. We're just going to use this entire thing, and it's just going to return it, and so we can pass it inside of this, and this will just actually print all the distances. So what you can see over here, so it's going to print out the updated distances like this, and it's also going to print out the previous positions, so you're going to see that as well. So since these both were dictionaries, we're going to use enumeration as keys to get the values of all of this, and it's just going to give us the key and value pairs, and it's going to be pretty cool. So these both are going to be allowing us to print these structures, so we're going to add this process here. So let's just create this call. So we had this test graph, and what we want to do is we want to use this method here, which is Dijkstra. So to use this, we have to pass that inside. So we're going to use Dijkstra here, and we're going to pass in the test graph. Also going to pass in the starting vertex, and that is A, because over here is the first vertex, and that's going to be our starting vertex. You could set anything you want later on, and then after that, we're actually calling this inside of this method, which is Dijkstra result printer, since it's accepting a dictionary array of D. So I'm gonna paste this thing inside, and we're gonna wrap it around the Dijkstra. So there you go, and this will just print out the things. So cool. So now let's run this code. So let's go and add in CMD here, and let's run this code. So Java C Dijkstra.java, and then let's just run it using Java Dijkstra. Alright, so we have an error here, something null pointer exception. Okay, we want the shortest path between two vertices. To calculate that, we'll just create a new method here, and we'll call this as public static void, and we'll call this as shortest path between. Inside here we'll have a graph, graph, and we'll call it as graph g. We're also going to have the vertex, and we're going to get the starting vertex, and we also need the targeted vertex, so we're going to say target vertex here. We have the shortest path between method, in which we're going to input the graph, the starting vertex, and the targeted vertex, because we want the minimum distance between two vertices. So we're going to use this method for that case. We're going to have the dictionary array object here, and we're going to call this as Dijkstra's dictionaries, and that will be equal to the dictionaries. So we're going to call the Dijkstra method here. We're going to call it using the graph and the starting vertex. What actually it gives us is the distances and the previous dictionaries. And I'm getting an error here. It's actually Dij. The method Dijkstra is undefined for the type Dijkstra. So the reason why I'm getting an error here is because I don't have a k. So Dijk, and if I do that, I'm all set. Now we want to put the distances and previous in their own variables. So we're gonna have the scope for that. So I'm gonna say distances dictionary, and it will contain all of the values which we had, and then we're gonna manipulate this. So we're gonna say dictionaries, so Dijkstra, Dijkstra, and we have Dijkstra dictionaries, and we have this sub 0 that will contain our distances. And for the second one, we could have that as 1, and that will be our previous. Awesome. To get the distance of our target vertex, we could say distances dot get, and we need to get the target vertex, and we want the value for that. We could say get data, that will return a string, and that will actually map us the value from our distances, which will be something like the value what it will take for us to reach from A to that point, and that we could store in some variable called distance. So make sure you have the type set to integer here, and then that should go away. Now what we want to do here is we want a print screen that will just show us the shortest distance path between those two. So what we could do is we could paste this in, and this is just going to print out the shortest distance between the starting vertex get data and the target vertex dot get data. So just between the two vertex, this is just gonna give us the letters, you know, the distance between A to whatever, and system.out.println will just print us the distance which was inside of the target vertex. Now we actually need the generated path that we should follow. To create the path, we could create an array list first, and that would be of type vertex, and we could call that as path. We initialized an array list to get the target vertex and assign it to a variable is very important here. So we're gonna have target vertex and assign it to a variable. So we're gonna go from the target vertex to the starting vertex. It's a bit like the reverse linked list. So we're gonna use some kind of functionality like that. We're gonna use a while loop, and we say while the v, the vertex. So if the v is data and the get data, we'll pass in a string. I'll say if that is not null, because we know that the first one, which is the starter will, is null, we're gonna add the path. So the path is actually the array list. We're gonna say the path dot add. We're gonna add a 0 here because the path is actually making us add something inside of this. So we're gonna add in a 0, and this would mean that it will be popped in the forward direction. It's not gonna go backwards. It's not gonna queue there, but every time a new value exists, it will come in the beginning. Every time a new value is added to this array list, it will be added in the beginning. So path.add 0 will be added, so every value will be added to the beginning of the queue, not the end. And the other thing that we want to do is we want to pass in that v, so that vertex that we said will be also passed in here. And then the next step here is to get the previous instance here. So we can say previous structure, which is a dictionary, dot get, and what we need is the data here. So we say v dot get data, and that would give us a string, previous dot get, and we got the value over here, and we're gonna assign that to the vertex. So since we have that get process here, we could actually need the vertex here, and that will assign to the vertex. So it's just gonna keep going like that. And after this while loop, we could just print out system.out.println the shortest path, and what we'd have now is the shortest path as well. So we could go from vertex from the path structure, which is over here somewhere. So vertex path vertex. So we have this path, which is this entire array list that now contains all of the vertices for that directed path. Now all we're going to do is iterate through this for every path vertex. We're going to print path vertex.get data, and that would just print us the letters of the corresponding path. Now the only thing that I'm going to do now is, like I said, I called Dijkstra result printer, and I passed in these two. So what happened here was that I was on an error, and whenever I was running this code, I was getting this error over here at line number 26 and 94. So over here in line number 26 and 94, it doesn't give me any clue of what's happening, but you could tell that alternative is less than distances.get neighbor value. So I was looking at the alternative value very carefully. Here I noticed that I did get an error while I was doing this. So this is actually a syntactical error. I was trying to get the alternative path distance, and I was getting the value from the distances dictionary, and I wanted to current.get data, and this was gonna actually give us the value for this one. So I didn't need this parentheses over here. I actually needed that closed here, and now it was just gonna give us the value here, which was string. So it was gonna give us the value of that current data. So it's just gonna be an integer here, and then that was going to be added with the edge.getWeight, so that will also be an int. So both of these ints added will result in this alternative value. So now it's proper, and if I run the code now, you can see now that this created it for me. So here what I had was these vertices, 1 2 3 4 5 6 7 vertices, and these were the connections to them. I just called the Dijkstra method, passed in the test graph, and put it in the starting vertex, After that, I use the shortest path between method, and this is all showing up. Pretty cool. So now we go test it out and see over here that the distance is updated, and it's according to what these vertices are. So these are, I believe, 7 vertices, and over here we have the connections to them. So you can see A is connected to C, A is connected to B, A is connected to D. And what you can see over here is that the previous, here we have A as null, and the rest, when I said A is connected to B, D, and C, if you look at B, D, and C, they're all connected to A. So D is connected to A. So over here you can see that this is the structure here where we have all these vertices and their corresponding values. So these are all the values that have been updated. So the distance from A to itself is 0, the distance from A to G is minus 38, the distance from A to F to 20. So we just passed in these values here, and it just allowed us to get the minimum distance from this graph. It's just telling if the distance from A to B is, so the minimum distance from A to B is 3, the minimum distance from A to D is 4, and so on. Over here in the previous, we have A has a previous of null, but the rest vertices show their previous vertex as well. For the last method that we created, we want to call that shortest path between test graph, and we get the starting vertex and the target vertex. Now we want the path shown and also the shortest path. So what we could do is short path, we pass in A and G, and this is going to call this method over here, which is going to call that method, and it will return us some cool looking path here. So we'll clear the screen and then run it and then see the shortest path. Here we got the shortest distance from A to G, which is correct. We got A to G and it was minus 38, the shortest path, and it showed how it was working here. So A to D to E to G. So if we map this out and draw this in a diagram, or if we look at it, everything will be correct according to these results. And that actually sums up our video.